All right, so we are on this second formative 2.6 to 2.9. This first question is quite long. I'm not really a stickler for vocabulary words, but in this case, I do think it's important to go over them at least. I didn't put them on a summative because I'm not placing too high of a value on it, but I think it's really important to still know at least these properties and how numbers can interact with each other when we're multiplying, adding, or subtracting. Most of these you already know, and it should be pretty common sense. It shouldn't be too much of a struggle. We're remote, so obviously you can use your book to answer these. It's not like I'm keeping it a secret from you. So listed below are 6 pretty common properties, and they were discussed in sections 2.6 and in 2.7. I want you to explain the rule in your own words and give an example to support your explanation. The first one's done for you to refer back to as an example. Originally, I was going to have this as a matching type question, but then I decided not to. I didn't want you guys just to match them. I thought explaining it in your own words was more beneficial. I know when I was in high school, I did not understand the properties or the rules the way that they were laid out in textbooks. I liked it when my teacher explained it in their own words and then gave me an actual example using numbers and not just A plus B. I thought that was really confusing. So for the first one, the commutative property of addition, A plus B equals B plus A. Explain in your own words, the order in addition does not matter. So to give an example, 2 plus 3 equals 5, and if I flipped the order, 3 plus 2 also equals 5. For the second example, the commutative property of multiplication, we have A times B equals B times A. Similar to the commutative property of addition, the order in multiplication does not matter. So we could have 6 times 2 equaling 12, and flipping the order, 2 times 6 to also equal 12. The associative property of addition is saying A plus, and then in parentheses, B plus C equals, parentheses, A plus B, parentheses, plus C. So for this one, when you have 3 or more numbers being added, the order in which you add them does not matter. So if I threw some actual numbers in there and I had 2 plus, and then in parentheses, 3 plus 5. So the parentheses I have to do first. So 3 plus 5 would give me the 8. So 2 plus 8 equals 10. Or if I flipped the order and I put the parentheses around the 2 and the 3, I'd have to add the 2 and the 3 first to give me 5 plus 5, which still equals 10. And then similarly, if we used multiplication, A, and then we were timesing it, B times C, or if we did A times B first and multiplied by C, when you have 3 or more numbers being multiplied, the order in which you multiply does not matter. So if we wanted real numbers, I'm multiplying the 3 times the 4 first. So I have 2 times 12 equaling 24. If I moved the parentheses to do the 2 times 3 first, I would get 2 times 3 is 6, times 4 is also 24. So the order of the parenthesis did not impact my final answer at all. The distributive property of multiplication over addition. So I'm distributing the A to the B and then to the C, and I'm doing that over an addition sign. So what that's saying is multiplication can be distributed over addition. It does the same thing as adding first and then multiplying. So I thought that explanation was a little difficult. I took it pretty much straight from the textbook. But if I threw in some actual numbers, I can distribute the 2. I can go 2 times 3 is 6, 2 times 4 is 8, 6 plus 8 is 14. Or I could add first. I can add the 3 plus the 4 first and get 7, and then multiply by 2, and I still get 14. Similarly, if I did that with subtraction, everything is the same except I'm distributing over a subtraction sign. So multiplication can be distributed over subtraction. You can also subtract first and then multiply. So if I had 4, I could distribute it to the 3 to make 12, distribute it to the -2 to get -8. My answer's 4. Or I could subtract the 3 minus the 2 first, multiply by 4, and I would still get 4 as my final answer. Moving on to the next one. Explain how the commutative and associative properties can be used to make the following computation easier to perform. So the commutative are the first two, the associative are the second two. Pretty much is what it's saying is that the order in which we add does not matter. The order in which we subtract does not matter. So in this situation, I can rearrange the order so that I'm doing all of the addition together and then all of the subtraction together. So I rearranged, I put all the addition numbers together, I grouped them, and then I put the subtraction on the end. Instead of add, subtract, add, subtract, add, subtract, add, subtract, I did it all at once. So then I'm going to group the addition, I'll add all those up, and I get 43, and then I can add all of my subtractions up, and I get -19, and I get the answer of 24. I could also, like, -5 plus 8, solve that, subtract 2, solve that, add 10, solve that. That's quite cumbersome and takes a long time, but if I rearrange the order, it goes a little bit quicker. The next one, we're going to simplify. So I'm using the distributive property, and the first set of parentheses has 3 terms, and the second one only has 2. So I find it easier to distribute to the going towards the left. So I'm actually going to distribute the 3 to each of the 3 terms in the first parenthesis, and then distribute the -x to the 3 terms in the first set of parentheses. You could do it the other way if you choose. I just think this way is a little bit easier, at least for me. So I distribute the 3. So 3 times 3x squared, 9x squared, minus 12x plus 6. And then I do the same thing with the -x, and I get -3x cubed plus 4x cubed minus 2x. And then I just need to combine like terms. The next one, 2 terms in the first parenthesis, 2 terms in the second parenthesis. So I'm going to distribute traditionally, I guess, to the right. So I'll distribute my -2x to the 4x and the -1, and then I'll distribute, so I did that. And then I'll distribute the 3 to the 4x and the -1, and then I can combine my like terms for a final answer. Next one, we need to simplify these 2 fractions. The way I like to do it is I like to split them up so that I have 2 fractions, each with the same denominator. So I have 4x divided by 6 plus 2 divided by 6. I can reduce those fractions to 2/3 x plus 1/3. And then I notice that, my denominator is still the same. So I'm actually going to combine them back together for a final answer. I'm going to do the same thing for the second one. I'll split them up into 2 different fractions, and I can reduce. The 2/3 x doesn't reduce, but the 3/3 does reduce to 1. And I can't combine those back together, so that's my final answer. And then the next one is x minus 3 squared equivalent to x squared minus 9? If not, give the correct answer. So to see if they're equivalent, I'm actually going to solve or evaluate, I should say, the first one. So since it's squared, it's being multiplied by itself. So I have x minus 3 times x minus 3. I distribute, FOIL, whatever you want to call it, and I get x squared minus 6x plus 9, which is not equal to x squared minus 9. So what this is saying is you cannot distribute a squared over subtraction or addition. Okay, I know that you can just The distributive property was distributing a number or a variable in the front over addition, but we cannot do that. We can't apply that same thing to an exponent because an exponent means that we're multiplying by itself. So they are not equivalent.